Hi, I'm Carlton Coffrin. In this video, I'm going to review a presentation from the IEEE PES General Meeting in 2017 at the second annual Task Force meeting on benchmarks for validating emerging power system algorithms. This talk is essentially an update of what's been going on in the task force for the past year and where we're going in the next year. The talk outline is as follows. First, we're going to do some announcements relevant to the PES General Meeting. Then we're going to give a progress report on what we've been doing for the past year, and this will include a deep dive into the first benchmark repository on ACOPF, and then we'll discuss activities for 2017 and 2018, and then conclude with some discussion of various parts of the ACOPF repository that we may consider changing in the future. So first, let's begin with announcements. So this year, the task force organized a panel session called Recent Developments in High-Fidelity Large-Scale Power System Datasets. It was on the last day in the last possible slot, but we had an all-star panel with amazing researchers from a number of great institutions, and overall the panel went very well. It's important to note that there was also a related panel just before that panel on the importance of benchmarks to drive innovation in grid modeling. It was also a very interesting panel on similar topics that's worth checking out. It's important to note that there's also a bunch of recent developments since the last meeting of this task force that may be of interest to anyone who's interested in the topics like this. A new version of the RTS96 network is being developed by people at NREL, and it's available at this particular link. There are some new synthetic test cases coming out of this particular grid data project at Texas A&M. There are some more realistic ACOPF test cases coming out at this URL at the University of Michigan, and a couple of different grid repositories have been proposed, including this bettergrids.org and also egriddata.org. So the overall thing is that this is a very exciting space, so it's worth paying attention. In the next couple of years, I think there's going to be a lot of very exciting developments in this general area. So let's get on to a progress report of what we've been doing over the past year. This was the 2016-2017 timeline that was proposed at the 2016 PES General Meeting. And more or less, we have met every one of these goals. The only significant change is that that was hopefully done in the third month. It actually happened more like the 6th month, but it's basically been completed at this point in time. So right now, we're in the phase of reviewing a living repository, collecting feedback, and just making sure that there's no major objections to what we're putting together for the ACOPF repository. So given that, let's just jump right in and look at Power Grid Lib, ACOPF benchmarks. So just as a reminder, there are 3 essential ingredients to begin building a Power Grid Lib repository. First, you need a specific problem formulation. And when we say specific, we really mean algebraic equations. You have to state this is the very specific particular problem that these test cases are designed to benchmark. Then you need to standardize data format so it's very easy for someone to run their algorithm on all the test cases in the test suite. And last but not least, all of the data needs to be released under Creative Commons licensing so that it's very easy to remix and redistribute and remake the test cases in the future. So let's look at, for the ACOPF problem, what do we have? This is the particular mathematical formulation that we're focusing on for the ACOPF problem. I don't have time to go into what all this math means, but there is a link at the bottom of the slide to a paper where this is all described in detail. But I will go over each of the sections at a high level. So we have quadratic fuel cost curves. They can also be linear, but the most general form is a quadratic one. We have box constraints on the generator limits. Both active and reactive power take the form of a square box constraint. We have bus shunts at the nodes, transformers on the lines, line charging on the lines, and then 2 types of line constraints. There's a thermal constraint based on apparent power and an angle constraint based on phase angle differences. The next step is what will be the data format that all of these test cases are provided in. And of course, we've selected map power as the data format because this particular tool is basically the standard for power systems baseline of AC power flow and optimal power flow. So that's the most natural data format to standardize around. And then let's just review for a moment the different networks that we were able to assemble for this archive. In total, we have 36 networks coming from various sources, and they range from 3 to 13,000 buses in size. That's quite a significant range in size. And this pie chart is showing the percentage of cases which come from different sources, and I'll just go through each of those particular sources. So the IEEE cases include the RTS case and some other cases which come from seminal papers that have been studied for a long time. The UW cases come from what many of us know as the Power System Test Case Archive, which was originally hosted at the University of Washington's website. This includes like the IEEE 118 and the IEEE 300 test cases. We have two test cases that are called PES test cases. One is this very recent 200 bus Illinois synthetic case, and another one is a WEC 240 case, which came out a number of years ago but hasn't been very widely used yet. They're the famous Polish cases, which were produced by Roman Korab, so we've included those. We have a number of RTE cases that come from a 2016 archive report, and then additional RTE cases, or these PGACE cases that were released by RTE and are currently distributed with MatPower. Now, the important thing, and a lot of the work that we had to do this year, was that all of these test cases are now released under Creative Commons BY, so that they have a license which is very amenable to academic research and algorithmic validation. Now, an important message from this Nestor report that was produced in 2014 was that in a number of these test cases, there is missing data. So it's important to fill in that data with reasonable values before you can start benchmarking your algorithms. So in the Nestor report, models are proposed for generator cost functions. Some of the networks don't even have those. Generator reactive capabilities, line thermal limits, and line phase angle limits. So I'll just quickly go over for each of those different test case categories, what modifications have we made to basically get them to all have a consistent set of data. So first off, all of the test cases have been given general phase angle limits of plus or minus 30 degrees. I was able to verify that if you do this, it doesn't remove the optimal solution from any test case, and in fact it's extremely generous. Sometimes in many test cases, more like 5 or 10 degrees is what you would expect from a transmission system. The cases which come from IEEE, so mostly the RTS 96 and other seminal things, they are mostly untouched because they included all the data that was necessary. The cases from the UW archive we've added realistic thermal limits, reactive capabilities to the generators, and also generator cost functions, all of which were omitted from the original archive. In the case of the PES test cases, we've added general thermal limits to the WEC case. And in terms of the Polish cases, we've added some additional realistic thermal limits to the 3000 bus networks. For the RTE cases, we've added generous thermal limits to any lines that didn't have them, and the same is true for the PGACE cases. So in total now, we have 36 networks, each with their one load profile and some realistic data. But this is unfortunately not an ideal number for doing algorithmic validation. We would really want something more like 100 to 300 test cases to be able to do this kind of validation. But at this time, I believe we would be hard-pressed to find any more networks that we can release under Creative Commons. So at least until the ARPA-E grid data program is complete, this is kind of all we have. So what we've done is we've used the same approach that the Nesta archive has used, which is just a stopgap measure until we have more realistic data set available, which is that we're going to use these 36 networks to generate additional test cases that are potentially more interesting and challenging. So what we're going to present is active power increase benchmarks, which are called API, and then small angle difference benchmarks, which are called SAD. And these are discussed at length in this technical report. So you can go and look there if you want more detail. But at a high level, this is how these test cases are generated. For the active power increase benchmarks, we linearly scale up the active power of all the loads, keeping the exact same load profile, and then we stop when the model would become infeasible. So some constraints, either the thermal limits or maybe some generation reactive power constraints, are coming into becoming constraining, and that's what causes these to kind of have a congested behavior in them. In the small angle difference benchmarks, we reduce the phase angle difference bound on all of the lines. So it's by default it's 30 degrees. We're going to increase it uniformly on all the lines and then stop when it becomes infeasible. Now you may be thinking, well, these are pretty arbitrary ways of making test cases, and you're right. There's no reason to think that these are useful or interesting approaches to making interesting test cases. But fortunately, in this particular technical report, we showed that these particular cases sometimes have very large optimality gaps when used with convex relaxations like the SDP relaxation. So this would indicate that there is something non-trivial going on, and they are quite challenging for evaluating, say, the optimal power flow problem. So if you include all three of these categories, we have a total of 108 test cases. This seems like a reasonable number, but I think we should be looking to grow this in the future. Like I said, maybe 100 to 300 is a reasonable range. And ideally, it would be nice if we were in a position to filter out easy cases and really focus the community's attention on particular open cases that are really pushing the frontier of what the algorithms can do. Now, it's important to talk about test case validation because we don't want to standardize or encourage the community to standardize around test cases that have any particular kind of strange properties. So what we've done here is I've made sure that every single test case can converge with an AC power flow, and also tested it with a DC power flow and also some convex relaxations. So inside of the repository, there's a file called baseline.markdown, and it includes this basic information. So essentially what you see here is that you have, for all the test cases in the archive, some basic reference results, both in objective value and runtime. And then you also have a list of tools which tell you what you need to reproduce the results that are in this table. And one really exciting thing about this is we've gotten to a point now where everything is 100% free and open source and available on GitHub. The algorithms, the test cases, and the solvers. So what that allows anyone in the community to do is to replicate these results very quickly and easily. So I'll just show you the minimum number of steps you need to replicate these results. First, you need to go to this particular test case archive and download the archive. You can just click the green button and then click the download blue button to get all of the test cases, or you can check it out as a GitHub repository if you want to be able to update it in the future. Then you need to go to julia.org and download Julia, which is basically a free and open source alternative to MATLAB. And then inside of Julia, you just need to move to the directory where you installed the test cases, install a couple packages for doing power modeling and using nonlinear solving, and then you can immediately run an ACOPF on every test case in the archive and get the exact same results that appear in that table. So it's that easy, and I would encourage you to go give it a try if you're so inclined. So in developing this test case archive, we have to give special thanks to a number of people. So I'd like to thank Rich Christie for providing the UW networks as Creative Commons by, Roman Karab for doing the same thing with the Polish network, Jim Price for agreeing to release the WEC 240 case, and then of course all of the RTE staff by default releasing all of their test cases under Creative Commons by, which made it possible to integrate them as well. So now let's switch gears. That's kind of the end of what I have to say about this first ACOPF repository. Let's talk about what we're going to try to accomplish in 2017 and 2018. I'm proposing two core activities for 2017 and 2018. The first is to develop a report on these ACOPF test cases, and the second one is to curate new repositories for important problem classes that the community is currently interested in. So many of us know this IEEE Reliability Test System Task Force report from 1970 or 1990. These are very helpful and valuable tools for being able to understand what's going on in these test cases. So of course we should build a report similar to this for the efforts of this task force. The task force report I am imagining being a very collaborative process on Share-LaTeX. So anyone who's currently involved with curating the test cases is welcome to join and help out with that report. I'm imagining that it's going to be very similar to the Nestor report, which you can look at now, and include things like the problem formulation, the data format, quality control, and a review of these baseline results. I'm hoping that in developing this report, we can kind of make a template for how similar reports should be generated for new repositories in Power Grid Lib, and just kind of giving a structure for how these things can be done. Now, one thing that's very important with such reports is authorship. People tend to get very sensitive about authorship, so I just want to talk about that right now before we get deep into the process. What I'm imagining is that anyone in the task force who makes a significant contribution to curating or validating these benchmarks should be involved with the report. That would include the authors of the original Nestor report, because a lot of what we're doing here is building on that. It's also, it would be nice to have a representative from MapPower, because we're using the data format they've developed in curating these test cases. And then all of those people who contributed test cases that I thanked previously, I think they should also be on the report, because without their contribution, none of this would have been possible. I think it's also important to note that at the time of the task force, when we presented this, there was no objections to this particular set of rules for authorship. In terms of the other activities in developing new repositories, I'm imagining or hoping that we'll have some kind of stochastic OPF repository. Wind and solar uncertainty is a very hot topic these days, and there's a lot of discussion about it. So internally at LANL, we are doing a lot of this, so I can imagine that in the next year, we would be in a position to start to have a rough draft of a test case archive for this particular problem. And another important problem that I would love to see a repository for is security-constrained OPF. The current ACOPF archive is not N-1 secure, and that's a big challenge. But coming through programs like Grid Data and the Grid Optimization Competition, we're starting to see interesting security-constrained OPF formulations and the associated data. So I think we're very close to being able to put a repository together for that particular problem. And then last not least, AC unit commitment, or even just general, any kind of unit commitment, there's a shortage of data for that. And internally at LANL, we're also working on that. So I would imagine that there's going to be a repository proposed for that in the next year as well. But if you're interested in any of these topics, please contact me and I'll try to get you in touch with people who are also interested, and maybe you guys can collaborate to put together one of these repositories. So here's the timeline that I'm proposing for 2017-2018. Hopefully by the end of August, we should have the first official release of this ACOPF archive, the 2017 version. Then we'll move on to working on the draft of this task force report. So I'm hoping that the first draft of that will be done in about November, and then we'll continue honing it for a few more months, and then the final version would be done in about the around March in 2018. And then we may have to tweak these deadlines based on any kind of IEEE PES process deadlines, but my current understanding is that there's no significant constraints there, so we'll just proceed with this schedule. And then July next year, we'll have the next general meeting where we'll review what we've done. So that ends the plan for the next year. The remaining parts of this talk relate to various discussion points for this ACOPF archive and spots where we might want to change things or extend it in the future. And it's worthwhile noting that during the task force meeting, there were so many questions during the previous section of the slide deck that we didn't actually get to these discussion points. But since the meeting, I followed up with a number of participants and gotten their opinions and feedback, and gotten some answers to some of these questions. So in the kind of release of the first archive, we will have made decisions on each one of these points. So the topics that were discussed, or that we plan to discuss in the working group meeting, or the task force meeting, were the following topics. So there was a number of test cases that were omitted from the original Nesta archive, and I wanted to go through what those are and see if there was any interest in integrating those. There was some discussion of cost functions for the generator fuel cost model. Then there was also some interest in replacing cost functions in the RT and PGACE cases, and then potential extensions to the benchmarks, for example, with some kind of like a poor man's D curve or HVDC lines. So I'll go through each one of these in detail and just explain, what is a bit of the issue and why is this something that's worth thinking about. So inside of Nesta, there are a variety of different categories of ACOPF test cases. In this particular task force archive, I focused on kind of seminal and realistic networks. But there are more types of networks in this Nesta archive. For example, there are these radial networks, which are interesting because they're tree-shaped networks that have non-zero optimality gap using convex relaxations. So that's actually quite a tricky mathematical case to construct, so that's quite useful. But because they're radial and transmission level, it makes no sense at all. These are incredibly unrealistic. So they're very much like a mathematical curiosity, but quite useful to have around in some cases. There's also this class called non-convex optimization, which includes, again, a variety of handcrafted test cases which are not necessarily realistic. Usually they're quite unrealistic, but they show cases when you really need a non-convex optimizer and a convex relaxation is not going to work for you. So again, those could be interesting cases if you're interested in algorithmic development for non-convex optimization, but I omitted them because they seemed like on the border of interesting for this effort. The last category was this utility cases, which includes networks from papers where the results have been checked and they are reproducible. It also includes test cases that are good for unit testing software, for example, small networks that exercise all the possible component features. And then they include some examples of networks with really strange behaviors, like if you add a line to the network, you increase the line losses, things which, are maybe hard to construct, but it's useful to have them if you're curious about how to do that. So one of the main reasons I omitted all these cases is that a lot of them are very close to my personal research interests, and I'm not sure they're sufficiently useful to include in like a more general purpose ACOPF benchmark library. And I don't want to mislead the community by saying that these are realistic when maybe they're only of algorithmic interest. So that's the reasons why I chose to omit them, but I'm open to having a discussion about integrating them back in if people find that they're interesting and useful. Let's talk about cost function units. If you read the original Nesta report, you'll see the equations I used for computing the potential cost functions from data are fairly simplistic, and Dan Malzahan had mentioned that he thought there were some improvements that could be made, and I don't think this will have a significant impact on the algorithmic results, but it would be nice just to add that additional bit of realism if it's fairly easy. So I've been currently working with Dan and following up with him, so it looks like this change will happen, and it's just a simple scaling based on the fuel type of the generators. This next point is a little bit more subtle, and so it has to do with the RTE and PGACE cost functions. In the RTE and PGACE cases, the fuel cost function is all set to 1. So essentially, you're solving a loss minimization problem. Now, this is a very reasonable thing to do, and from a network operator standpoint, maybe that's all you care about because the dispatch has already been set by the market. But there is an issue, which is that particular cost function is a very special case of the whole AC optimal power flow, and it seems to have unique mathematical properties. It seems to be particularly easy of all the cost functions that you might consider. So we might be introducing some bias there by having so many of these realistic test cases having this specific cost function. And so the question is, should we replace this cost function? It's standard practice on the other cases to have a linear cost based on US fuel prices, but it's not 100% clear if we would be damaging these test cases or not if we replace that. I think a good comment that was brought up after the meeting was that if we replace these cost functions with something that's more interesting, like some fuel-based linear cost function, we can always tell people if they prefer to study a loss minimization objective, they can just ignore the cost function and make it one everywhere. So potentially adding the additional information of some reasonable cost function is not hurting anything. So anyway, these test cases are curated by really smart people very recently, so I'm hesitant to make any significant changes to them. So another interesting question is a potential extension to these test cases. So Matt Power has recently added support for a basic kind of HVDC line. The model is described on the right-hand part of this slide. Essentially, it's just an active power pass-through with a linear loss function. And what I hope to discuss during this meeting was, is this a realistic model? Should we be trying to integrate or find more test cases with this kind of data in it? Right now, there isn't that, none of the test cases have DC lines. So it's not clear if it's necessary or helpful at this point in time, but it's definitely worth considering, maybe in future revisions of this ACOPF repository. Another thing to consider is the idea of what I would call a poor man's D-curve. So we all know that in practice, generators are limited by a D-curve in their P and Q outputs, but in all of the current test cases, P and Q are just a box. So there isn't a link between the P output and the Q output in a particular generator. Basically, they're two independent variables with their own bounds. Now, inside of the Matt Power data format, you have fields for what I would call a poor man's D-curve. It's a trapezoidal shape like the one illustrated in this picture. So we could look at maybe fabricating reasonable poor man's D-curves for all of the test cases. So Dan Mosleyhan has done some work to basically construct reasonable D-curves based on the generator parameters. So this is another extension we might consider, and it's not really clear to me if it's important or not, or how it will affect the test cases or not, but definitely something that we could think about for the future versions of this archive. So that's the end of the discussion points. I hope this talk was helpful and interesting, and if you found anything in it particularly interesting, I encourage you to reach out and get on our email list, and then potentially attend our task force meeting at the next general meeting. Thank you very much for watching.